Yeah, good evening. Welcome to the section 4. So we're going into the ML workflow and the Python for AI ML. We'll be doing model training and also evaluation. So for tonight, we'll be diving more into the hands-on part. Also maybe at the end of this video, and when it's been uploaded on YouTube, there will be a link added to it where you can access the materials being used for this section, because some other jottings has also been done. We have the ML notes 1 and also notes 2, because there are a lot of basic foundations things we need to know that because of time, because we just want to get into the hands-on, we are not able to dive into properly. So these jottings or these notes is just like a summary of them. So I'll be referring to them maybe once in a while when I mention some terms or things. So let's just continue. So we'll be starting with the complete ML workflow. So I believe we've already in the first section, we've talked about the data science workflow. So the data science workflow and the ML workflow, they are similar and almost the same. So this is just a step-by-step process where you take in raw data, just like we discussed in last session, where you have your data mining, where you also process your data. Or beyond processing your data and doing the exploratory data analysis, you now move to what? Building model, that is model training, evaluation, and development. So just a summary, you have the data collection where you gather your data, whether from a database, API, web scraping, or anywhere. Then you prepare your data, which means you clean, normalize, or encode. You split your data also into the training and what test sets. The common ones and splits we have is 80-20. We have more than that. We will also see when we dive more into the section coming. I think we have a part here that talks about the ways we can split our data sets. I'm trying to get, yeah. So we can see there. Sorry. Yeah, pressures, you're welcome.
Good evening, sir.
Yeah, you're welcome. So I was starting with the section 4 and explaining what we are going to do. So I was talking about the data preparation where you clean, normalize your data, where you also split your data into training and test sets. You have the 80-20 split, and I said we also have different types. It's based on your choice. So that was what I was trying to show you. And I believe you've seen the link sent to the group where it has contained the link to a drive. So you can get all these materials there.
Yes, sir. Yes, sir.
All right. Okay. So, sorry. Yeah, this is what I was trying to explain, the data split. The split options we have the 70. Normally, most splits, you can either have a train, validation, and test set, or sometimes you have a train and just test set, like this option C. You don't have a validation set. So when you don't have a validation set, the best way we usually split is 80-20. Sometimes we have 70-30 because no validation set. But when you're having a validation set, you can have 70, 10, and 20. Your validation set will be small. The reason for validation set, your validation set is still like part of your training data. But the thing is, after you've trained your model, you use your validation to test your model to see what is the accuracy, to evaluate your model. So when you use it to evaluate if it's performing very well, you go on to use your test set. But if your model is not performing very well, you go on to retrain. So Because if it's not performing very well and you go on to train again, that is your model have not seen the test set. So by the time you are using the test set to test your data, you are sure there is no data leakage. When we are talking about data leakage, means your model have seen, like it has seen the answer, just like giving an expo to your model. That is what we mean by data leakage. So that is the essence of validation set. So you can still evaluate your model with that before now proceeding to using test set. But in the case where you don't have a validation set, you just have a train, you've trained your model, you will need to check and see if your model is performing very well. So you use your test set. But what about in cases where it's not performing very well and you now need to still do some things? Sometimes your model is like might have seen the data or the test set here. So that is the essence of validation set. So don't fit your training data to obtain maximum accuracy. When you are evaluating, we have what we call loss. Loss means error. It's just like error. What is the percentage of error you are getting? So the lower your loss, the loss is like the error. The lower your loss, then the better your model is performing very well. If the lower your loss, accuracy is increasing. If accuracy is increasing, loss will decrease. If loss is increasing, your accuracy will decrease. It's just like opposites of each other. So you don't focus on the accuracy on, yes, your training model should have an accuracy, but it doesn't need to have the maximum accuracy. Where the maximum accuracy should try and come from should be in the validation or test set. It will show you what, can you say, rather focus on the accuracy of your validation or test data. That is it. So that is what will give you the true state of your model, whether your model that you are building is good, is good, is better, because your model can have a higher accuracy in your train set, but when you validate or test it, you'll be having a lower accuracy. That means your model just did like cramming. It didn't really learn anything. It was just cramming. So that is for that. So another thing is 80% of your code might be in the preparation of your data set. Only 10% is for your building model. So that's just like some things to share. So now let's go back to the material we are using. So we are talking about model training. Now we've done data preparation, we've done all this last time. So now you now have the model training. So this is where you feed your training data, the data you've prepared, you've cleaned it, you've normalized, you've encoded. Though we didn't do encode the last class, we all do encoding and splitting data today. So we will just take a data that we believe data is already clean and normalized. So we'll just do encoding and splitting the data. So we'll feed this data now into an algorithm. I explained the algorithm you have based on whether it's a supervised learning, is what is an unsupervised learning or reinforcement. Each of them have their algorithm. For supervised learning, we have regression, we have classification. Even for classification, we have logistic regression. For classification, we have decision trees. So these are algorithms. So after we've trained our model, in the time where you are training your model, it's the model try and do something. It adjusts the internal weights thousands of times until the errors are minimized. So I'm coming. Let me see if I should explain the simple maths there before I go to our code. Okay. So I will explain that later. Then in the last step, which is evaluation and deployment, is where you now test your model on seeing 20%. This is your 20% test set. Sometimes it can be 30%. You will test your model on that, your test set. No matter the percentage you give it can be 40 sometimes. So when you test it, you measure the accuracy, you measure the precision, you measure the recall. All these terms you might not understand them now. But when you check through all the additional training materials, you see them being explained. Then when your model is performing very well to a satisfactory level, then you can deploy your model as an API or as an app, or you even add it into an existing website or an app. So I'm coming, I'm trying to see where accuracy and all that is being talked about. So this is just an additional thought that talks about the different methods of machine learning. We also have natural language processing here. Yeah, we have classification. Okay. So today, basically, what we'll be doing is the classical machine learning, where we'll be using we won't go into decision tree today. In the next section, we'll do that. We have the decision tree, linear regression, and logistic regression. This is used for classification. I'm trying to find an area that talks about recall and all that. Okay, this confusion matrix, we'll use this later. Okay, let me just leave it at this part and check these other materials. Okay, this is what I was trying to say. So precision, now when we are talking about precision, yeah, precision and recall. Precision means the fraction of the correct positive. And when you are talking about precision recall, you need to understand true positive, true negative, false positive, false negative. You can get this in your confusion matrix. You can see them in confusion matrix. True positive. So that means if your model is predicting something as positive, is the actual result positive? That means it's a true positive. Let me see the language being used here. I said correctly predicted positive. If your model is predicting something as negative, is the actual result negative? So that is what true positive means. But false positive, your model is predicting something as positive. Meanwhile, the actual answer is what? Negative. That is a false positive. For false negative, your model is predicting it as a negative, while your actual result is what? Is positive. You can see that. So this is the formula for calculating precision. This true positive, false positive, and all like that. So we'll get into it when we start building actual models. Not to waste time, because I want us to go hands-on today. If you are seeing hearing me, just give me a thumbs up. All right. So now we'll be going into how a model training works. So during training, we will select an algorithm. The algorithm now will see the training example, which is from our data, our training set. It will make a prediction. Then it will compare it with the correct label. So in that training set, we will give it the answer in the training set. It has the like the question and answer. So it will train. So by the time it's trying to now learn what is the relationship between them, we will try and do a simple program on that hello ML word. You will see how it works. So it's not predict and learn. So in doing that, it will be adjusting its internal weight to reduce error. So by the time it's adjusting its weight, it will keep doing that until it's able to find the correct weight. W is unable to find. Once it finds the correct weight, then it applies it for the next, maybe in the other training and test set here. So this process is repeated thousands of times until the model converges. When do we say the model converges? That is, the errors are minimized. So the mathematical technique used to adjust weight is called gradient descent. So this is called gradient descent. So gradient descent is just a method used for adjusting weight. It's an optimization algorithm just to minimize our loss, to adjust weight. So let me show you a simple calculation here. Is in a simple math calculation. So let's say we have let me change the color to red so we can see, and this to like 12, 14. So you have y. I believe you know this in mathematics, where you have y equals to ms plus c. You've seen something like this before in your maths.
Yes,
This
sir.
m is your gradient. Yeah, m is your gradient, yc is your intercept. So that is the same way It works in just a simple scenario now. Let's say for regression, your y is your output. Your output, your x is your input. Inputs. So now we will be having w. W will be our weight. So this is in simple time. In some of these kind formulas you've seen, sometimes you'll be seeing only y equals to ms. Sometimes there will be no intercepts. I don't know whether you've seen some like that. It doesn't have
Yes, sir.
intercept, only have this. Yeah. So let me introduce one more time here. Let me put it here. You also have your b equals bias. So that is just the same way it is. You have your y equals to wx. So w is your weight. And in some scenario, most time this is the complete formula. It has equals to wx plus your b, which is your bias. So what it does is initially, maybe when your model is running, it predicts the w. Let's say w, our weight is 1. Maybe our bias is 0. Then it has the question, which is like the x, the input. It will not try and apply that weight to the input, add the bias, and see if it will get the answer. If it's not getting the answer, it will try and guess another w and apply it. It will try and guess another bias. But this one is where the major work is in the weight. So it will keep doing that through a method called what? Gradient descent. Gradient descent. I have some images. I don't know. Maybe I'll just go online and try and show example of the gradient descent, the way it works. Gradient descent. So it's through the method of adjusting, minimizing loss. It's called the gradient descent. Can you, okay? Okay, let me just use this, or let me use this. So I don't know, can you see this image now here? So let's say
Yes, I see.
this is where our minimum, you can see weight now. So maybe this is where our minimum loss is, where you have your minimum cost. Because the higher your loss, the higher the cost. It's just like you spend more money and like that. Let's just use it that way. So now you need to minimize your cost. Minimizing your cost means you're also minimizing the losses. So you can see that, let's say it picks a weight somewhere here. It sees that, oh, the cost is high, the loss is high. It keeps adjusting the weight until it gets to the minimum. That's just like the way sometimes it will get, after predicting from here, it can take something here and they still see that the cost is increasing again. No, it will mean that at that point it will, oh, I need to come down to be able to get to this minimum. That's just how the gradient descent works. Because of time, I won't be able to talk much on that. So that is for that. So the model starts with a random parameter. This is what I just explained now. A random parameter, a random weight. Oh, which number should I pick? Based on how I'm looking at this problem, let me start with 2. Let me start with 0. I hope you are getting me now. Then you now check the training example, apply that weight to the example, and makes a prediction. If the prediction you make, you now compare it with the actual label in our training set. So when it compares to it, it now calculate the error. Let's say it's like a number. This would be best described for a regression, a linear regression problem. Let's say the answer is meant to be 4 and it's getting 3. It will 4 minus 3. That is what? 1, difference of 1. So is the difference minus or positive? So that will tell it, oh, maybe it should increase its weight or to decrease its weight based on if the error is what? Minus or positive. I hope you are getting me.
Yes, sir.
So it will now adjust the weight to reduce the error. So using gradient descent. So it will keep repeating this until it gets a lower error. Until it gets a lower error, that is the model converges. So that is just how model training works. So this is just an example for random forest classifier using Python and scikit-learn. So we'll be using scikit-learn to build our model, but before that, we also have other libraries like PyTorch, and we also have a TensorFlow. So, but before we do the example in this, maybe we'll do that in the next session. I want to start with some simple model. So we have scikit-learn. These are some libraries for machine learning. TensorFlow, we have PyTorch, and we have some supporting libraries too, like NumPy, Pandas. You are familiar with all that. So this is random forest classifier. Random forest classifier is an ensemble model. It is an ensemble model that has what? Decision tree. Ensemble model that is composed of multiple decision tree. And what is decision tree? This is an example of decision tree. You have a root node. You have like a question: what is the age of this person? Oh, this person is less than 18. So if the person is less than 18, what is the weight? These are decision nodes. Oh, is the weight is less than 60. So this person has low risk of what? Of having a heart attack. If it's greater than 60, the weight, high risk. Or if the person is between this age, low risk. If the person is greater than 30, is he a smoker? So this is a simple way of making decisions. So we can also do that with machine learning. So mostly we use it for classification also. So the random forest classifier is just like containing multiple decision trees. It contains multiple decision trees, and there's a point where I mentioned a term now that random forest is an ensemble model. It has multiple decision trees, and what is an ensemble model is being mentioned here. Yet we also have ingredient descent. You can see it here, where you used to adjust weight and biases. So we have also have some other things, but when we get to neural network, we'll talk more on those ones. So I will mention something here too, but I just want to explain ensemble model part. Ensemble model. But what ensemble model means is when you combine multiple models together. So you can have bagging or stacking. But in these documents, can you see ensemble modeling? You see this now? Ensemble modeling here. So you have your bagging. When you use several versions of the same machine learning algorithm, be familiar with this word algorithm. So when you use this different version, maybe version 1, version 2, a tweak version, this is bagging. But for stacking, you use different machine learning algorithm, you combine them together. So you can see them here: decision trees, random forest, bagging, and boosting. So one other thing you also need to know is the term when we talk about underfitting and overfitting. So underfitting now is when your system doesn't work well with larger test data. You've trained your model, probably it might perform well or not. By the time you give it a larger data set, it's not even doing very well. That means your model has what's underfit. So, but overfitting is when you add complexity to your system and it's making it hard to handle. In this case, now you train your model and your accuracy, you are getting like almost 99% or 90% in your accuracy. But by the time you are not using a test data, the accuracy you are getting is like 20% accuracy. How come that a model that when you trained that is performing very well is getting 90 and you're having 20% in your test data? That means it has what overfitted. So that is for that. So you just need to balance the data to get the best prediction. So having set this, we will now be going into our hands-on. So if you are still with me, let me know. All right. So I don't know who just joined the call now. I might not be able to see the person, but I know someone just joined the call now. So we'll be starting with a project that I term LOML word, machine learning, simple ML model. So here I'll be using TensorFlow. Then we'll go to the other part. I will use scikit-learn. So now I hope we can all see this my screen. Let me know if you can see my screen.
I can see your screen, sir.
All right. So you can see this place that I gave a data. Now, I had to generate a data. We imported NumPy used to create an array. So you can see -1, -2. This is the input. This is the output. So based on this formula that I gave earlier here, where is it? Based on this, y equals to ms plus c, or whether ws plus b, anyone you want. Can you guess the formula for getting this? If you have 1 as your x and your y is 4, what is the formula that you use to get it? Can you just guess?
MX plus C. Okay, it's an obvious. So you're talking about from these formulas that you gave us?
Using this formula here.
Yes. Okay. Yes. What do you want me? What did you ask me to guess?
The relationship between these x and y. What is the relationship? Let's say we have 2x. If you have 2x, let's say our x is 1 now. So
Okay.
2 times 1 is what? 2. It's not giving
So
us
yeah.
4, right? This is not giving us 4. So let's try 2x plus 1. 2x
Okay.
plus 1. So if you have 2x, we are just trying to do like the way a model will learn also. So 2
Okay.
times 1 is 2 plus 1 is what? 3,
Okay.
right? So I'm just trying
Yes.
this first one first. Then when we get it, we try for the other. What else can we
Okay.
try again to see if we can get 4?
Oh, okay. Is it possible to use minus?
Okay, let's try. Okay, 2x minus 1, right? Or what?
No, 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 no. Like the X.
And you know our x is 1 here, or you want us to start with the -1. I'm starting with this 1 here. I don't want to
Oh,
start with
oh,
0
okay.
first yet.
Okay,
I'm
okay,
starting
okay.
with this one here. You can pick anyone to
Okay.
start with. It's your
Okay,
choice.
then that means we'll change the 1 to 2 now. The +1 to be +2.
Okay, let's try that. Let's try that. What would be the answer? 2 times 1 is 2. 2 times 1 is 2, right? Plus 2, that is 4,
Yes.
right?
Yes.
Let's try it for 2. Will it work? 2 times 2 is what? 4.
4,
4 plus 2 is what? 6.
6. Yes.
It's not giving us 7. We can see that.
Yes.
Let's try it for
Yes.
3. 2 times 3 is what? 6 plus 2,
Yes.
8. It's not giving us the answer. So what else can
Yes.
we try?
Okay.
What if we increase the values with our x, maybe 3x, and let's
Oh,
remove the
yeah.
plus 1. So 3
Okay.
times 1 is what? 3.
3.
Okay, let's add plus 1. This will give us 4, right?
Yes.
So let's try 3 times 2, 6, plus
Yes.
1, 7.
7,
Let's try for 4. 4 times 3 is what? 12.
12,
Plus 1,
13.
13. So it's like this is the actual form. Let's try for the minus. 3 times -1 is -3.
Yes.
-3 plus 1 is what? -2.
Minus 2.
So this is the formula that is the relationship between them. You can try it for everything. So this is the relationship. So now we did not tell our model what the relationship is. We want it to find out the relationship between them and predict. So now let's go back now. Since we've gotten the relationship 3x plus 1. So this is a model we are using. This is this is neural networks because you can see layers here. So I won't talk more on this type of model until we get to neural network parts. But now you can see an optimizer here, SGD. If you need more details, just check the notes that I've uploaded. I just added this ML notes 2 there again.
Okay.
We have ML notes 1. So that one will give us more details on those model. I think I mentioned it somewhere. I'm trying to see where I mentioned it. So it's an optimizer, SGD, stochastic gradient descent. That is the full meaning. You know, I mentioned gradient descent the other time.
Yes, yes.
Yeah, so it's just a method. So it's trying to ask which method do you want to use to minimize your loss. So it's an optimizer. So I can use Adams. We have another one that we use mostly, Adam. We use Adam mostly. If you check the notes properly, well, you see all those things there. You see them there. So then the loss now, we have different loss that we have. We have the RMS, this is MSE. That is the short form. We also have the RMS. We also have the MAPE. We also have the MAPE. I think I need to get this and show you. Not just mentioning them. MAPE. Where can I get all this? Maybe it's in the first one. Yeah, this is exactly what I was saying now. Can you see what I'm saying here? Optimizer and loss functions. You can see Adam,
Yes, yes.
SGD, stochastic gradient descent. We also have RMS prop. You can read about each optimizer. They have the advantage, and sometimes if you try this optimizer and your loss is increasing, you can say, let me try this one. Probably it will optimize my system and the loss will reduce. So when you select your optimizer, you also select a loss function. Is it MSE? MSE is mean squared error. We also have binary cross entropy. When you're working with I think classification model, we basically use this. When it's binary classification model, you use this. But when you have more than 2, you use this loss function. So each of these terms, functions, they have where they work best. Now, this thing now also be familiar with model.fit. This is to train your model. Why this is to predict. After you've trained, you want your model to predict the answer to another question or to another input. You use dot predict. But when you want to evaluate your model, to know where's the accuracy, what are some parameters, how well is it performing, you use model.evaluate. Hope you are getting it.
Yes, sir.
Then you also have the regression evaluation metrics. When we get there, we'll talk more about them. RMS. We might not be able to talk about everything. This MAP I was mentioning. So we might not be able to talk about everything today, or just get familiar with some of those terms. That's why I created this note for this as a kind of reference. So now we find the relationship between this our x and y. On the norms, we are meant to split this data set into training and test, but this is a small data. We created it on our own. So this was it. Let's say assume this is the training set. So now we now use model.fit, which I just explained. That model.fit is to what? To train, right? So you give it your x, that is your input. And what is your output? This is our output, this is input, this is output. So we are telling it this is the input, this is the label, the result. Then epochs means how many times you want to train your model. It's just like saying one complete circle. Let's say when you are drawing a circle, you draw from 0 to 360-degree, right?
Yes.
So it's just like when you have your data, how many times do you want it to go? Let's say sometimes you can have data set that have like 100 rows, 1,000 rows. So how many times do you want it to go from to go through all your data and keep learning? So that's like a complete circle going from the beginning to the end. So it will go from the beginning to the end. It will learn something. But by the time it goes just one time, it might not learn enough. But imagine it just like reading. When you read your course one time, you read it another time. By the time you read it like 10 times, then you will have known what is inside that book more than someone that read it one times. That's just like the way epochs works. So how many times do you want it to go through your data to learn? Yeah. So that is what we define here. If you put a lower epoch, you might be, if you have a large data set, you can use a lower epoch. It's better. But if you have a small data set, you might have to put a larger epoch because the data set is small, but it needs to go through it enough time to properly learn what is happening. So that is why we have epochs. I tried changing, try saying maybe the 500 is too much because there are some data set that is heavy. If you try to train them for 500 epochs, you might use 1 hour to train a model or more than, depending on how large your data set is. So that's why sometimes if you use 500 epochs, you might be doing what we call overfitting, just like I said earlier, where your model will learn and until it will start cramming. It will start cramming and start looking for something that is not there again because it has read everything and it start looking for problem when there's no problem. So that is why you need to be careful of how you use your epoch. Normally, you can just start with a small epoch, maybe around based on your data. If your data set is small, I said you use a high epoch. But at least you can start with maybe 100. You will see the results. You can see loss here now. You will see the results. If it's not performing well, you increase it until you get what you want. You can see when I started with 100, I'm trying to scroll through. You will see when it's in 100, you can see it's giving 0 point something in one cell. To me, I would have said having a loss of 0 is okay. But looking at this data set is small. So I try to predict the answer. Now we are not giving it in the value. Predict if x is 10, what will be y? Just like you now saying put 10 into this place. What is going to be y? So when you put 10 here, 3 times 10 is what? 30 plus 1. That is what? 31. That means our y is what? 31. So when I tried that, the model was giving me 32 at a point and all that. So I had to train for more time. So now if you check through, you'll be seeing -5. That is 0.00000. So at least I trained it up to 500 times and I predicted and I was getting 31.000 something. So if I decide to round up, I can say what my model has what learned. Can you see? 31.000. So I can round this up to what? 31, which is exactly the answer I should get when I apply this formula, right? I think I will try and copy this code and also put it on the training drive for you to, if you want to try it on your own. You can give it another relationship now. I will show you another one. Then something, I don't know if you saw this, but after we train our model, I said you use what? Model.predict to predict. And there's one thing I also mentioned the other time. You also have evaluate, but we won't be doing that now. So this is just a simple way of showing what machine learning does. So that's why I termed it LOML word. And I think someone did this. Was done by Alex. Yeah, Alexander, he did that. So for his own, he was trying to predict a pattern in a linear relationship. For his own data I gave it, it was what? 2x plus 1. You can see. Then he has to also train, I think he trained the model too. So now he has to use, okay, he also use optimizer SGD and all that. He trained for epoch of 500. And he also predicted if we got his own answer to 21.00 something. If it's 2x, he'll be getting 21. So now let's move into, we'll try and create a new, we want to create a new project now. So if you are still with me, let me get a thumbs up. All right. So now we'll be working with scikit-learn. So now, if you've not used scikit-learn, the first thing you might be required to do is what? To install scikit-learn. So, and scikit-learn depends on two important libraries, numpy and scipy. It depends on two. So sometimes if you are getting error, you might need to first install these two libraries, then you install your scikit-learn. If you are working with all these Google Colab, Jupyter Notebook, you might not have too much errors. They have some libraries installed in them to automate. But if you are working on your local machine, and I mean on your local machine, when you have your environment, your coding environment running on your own local machine, not on a cloud-based system. So you might have to install them on your local machine itself. So now let's try and install this. So let's try and install this to get started. So now we'll be, okay, let's get started. I'll call it getting started with scikit-learn. So after I'll also try and upload all this code on the app place with scikit-learn. So now let's install. We'll be running it together. So now while that one is installing, let's try and see what next. Okay, so let's say we've installed this. You can see you there. If the model is existing, it will upgrade it. So now, so we installed that. We now need to load our data set. So I already explained that your X is your what? We call it features. But X means your input variables, your input, while your Y is your output, is the result, is the value you want to predict. So we call Y what our targets, while X is being called features. So now, normally the way when you are working is to load your data set, we need to use, let me try and, okay. Let me try and enable scrolling. I think that's what is giving me, making it to skip some places. All right. So now, scikit-learn provides some building data sets like iris. This iris is just like a data set that contains flowers. So that is for that. And we use this data set for our model. But you might decide that you want to load your own data set. So maybe after this, if you're able to finish this on time, or if not, in next class, we try and load a data set of maybe a cat and dog, or any data set. I think, yeah, or maybe even an handwritten data set like the one Alex used in one of his projects. We'll load it using scikit-learn and we'll see that. So now let's check our code as it's installed. So it has installed, finish. You can see installing connected. It found an existing installation. So it installed that and upgraded to the latest version, which is 1.9. That is the advantage of the UI puts here. Upgrade. It will be update rather, yeah. Okay, so the next thing now is we will need to load our data set. Normally based on our process here now, we've done, we are meant to start with data collection. So let's say we have the data already. We are meant to prepare the data. But most times it depends on the places you are getting your data from. If you are getting some data sets somewhere, most of the work has been done. Your data has been cleaned and processed. So what you just need to do is what? You might need to do normalization, encoding, and splitting your data set. So I will assume our data set has been what? Has been cleaned. Yeah, and mostly it has been cleaned. So we'll just be going to this and model training. So now let's load our data set. So you can see now from scikit-learn dataset, we are trying to load an inbuilt dataset. So maybe later we'll be able to load our own dataset. I'll do that using pandas. So let me first copy this, then I'll explain this. So now, so what this is saying, we are trying to load the iris data set. So iris upload, we will load this. Let me put this somewhere else. So the future name, it will get the future name for us and store it. Iris dot the future name, store it here. Get the target name, put it here. So once you run this code in this code cell, it will print the future name, the target name. That is, we are trying to preview our data sets to know what is there. And this one will print the first 5 rows of our data sets. So let's run it. Are we still following? Yeah, all right. So the feature names in the feature names that we have is the sepal length. You know, I was saying this is like a flower data set. The sepal length, if you are used to flowers, they have like the sepal length, the width, the petals. Those are like part of flowers for those that did biology. So based on this length, width, you can know, oh, you want to predict what type of flower is it. So these are the features, those the sepal and the petal. So what is the length, what is the width? So we have 1, 2, 3, 4. Those four. Then we have what? When we check the shape, you see these 4 columns there. Then the names in our targets. We have setosa, versicolor, and vaginica. Those are the type of maybe the flowers also, the iris flower. So then we try and print what? The first 5 rows. So now looking at these 5 rows, this row 1, row 2, row 3, row 4, row 5. How many column? 1, 2, 3, 4. You can see it's X we print, type X. But let's say we put type Y, it will only print 1 row, which is the setosa, color, and vaginica. And I can decide to print everything. So now you can see this first one is about sepal length. The second one is about sepal width. The third one is about petal length, petal width. So that is how it is. We are trying to preview our data set. So when we are done with that, then we move to, so you can see what we have here. You can see the results, the output is also here. This is from Gigs for Gigs site. So we will now need to split our data set. This is where the major work is. When you check this training material, I said you will go to this project later on because this is an ensemble project. I've talked about it, bagging and all that. Can you see scikit-learn ensemble? So we'll be going to this later. But something was there. They imported this train test split. This is used to split your data. Now, the example here, they splitted their data into what? 80%, 20%. I mentioned that in the other that you can split it based on your choice, 70, 30 as you want. So now we need to import that also. We want to split our data sets. And I will explain some points here, which I want you to take notes. So now we import from this, we are importing train test split. Now you now notice this S train. This is, you have your train set and your test set. And in some scenarios, you might be having validation sets. But let's just stick with the simple one, which is a train and test set. So for your train set will have the features and it will have the targets. I believe you all know what those terms means. That is the essence of showing us some things. So your X is your feature, while your Y is your what? Target. So for your train set, this is the features of your train set, and this is what the target of your train set. Your test set will also have what? The features, and it also have what? The targets. You can see them. So you have the X part of your data and the Y part. Then you also now split that data into 2 again. The X part is split into train and test. So now you need to tell it, let me leave a space here. Split, split the data set. We are using 80/20 here. Data set into 80% train set, train, and 20% test. So how do you now give the percentage of training you want? You can see now that in this is your variable, just as if you are defining a variable name. I can decide to give this any name I want. Is your choice. But to make it easy, that's why we use train, test, train, test. You understand training and test set. And this X based on futures and targets, you can give it anything you want. So then we now bring what train test split. This is like the function inside the library we imported. Now import train test split. Can you see it? This is the function here. So now this X and Y is your data set. Note it, this is your data set. And we know our data sets now. We've splitted our data set into futures and targets, which is what we did here, X and Y. If I give this maybe X, just like we have here, you can see that I gave it X, X, Y, X. This is what I gave it. And this is what you are seeing here. You can see it here. So that is what we also have here. Because I just use X and Y. This capital X and this small letter Y. This is exactly what you have here. Capital S, comma, small letter Y. So now, because you want to split your data now, this is using 0.4, right? So let's use, because the data set is not much. So this one, they did 60-40% split. So let's do 70-30 in our own case now. Or let's do 60-40. You can decide to change it on your own. So now, we said our test set is 0.4. 0.4 times 100 is 40%. That is just math. Or 40 divided by 100 will give you 0.4. So once you automatically tell us the size of a test set, we automatically know that the remaining percentage belongs to your what? Train set, because you only have two sets here, your train and your test set. That's the two sets we have. So when you are telling us your test size is 0.4, then automatically your train set is what? 60. But if I should follow 80%, 20%, I'll put 0.2 here. Automatically, my train set is what? 80%. Hope you are getting that. And you are seeing this random state. Now, we don't want to have a fixed method of splitting our data set. We just want it to split it based on his own choice. So we just gave it a random state 1. But there is another thing here that I want you to notice here. You are seeing random state 42 here. That is now, this is like a seed number. I think we mentioned it in one of our sections that you want your data to be reproducible. So because I split this now, because I gave it a random state of 1, anytime I want to split that data set, maybe on your own system now, and you gave it this same random state, we'll be getting, or anytime I keep running that code, if I should disconnect this runtime and come back maybe the next few days or so, I want to still be able to run this and get almost similar answers. So that's why we are giving it a seed. I can give it 42. I can give it anything. But if I should come back the next time I run this project and give it a different random state number, I'll be getting a slightly different answer. It might be more, or I don't know. It won't be the same thing we thought I'm getting this first time. I don't know whether you get my point. So let me try and see something. You notice in this place I'm using now, they have their results. When you see in a place, you'll be having 0.866. I can run my own too and get exactly what they got. So far, we are using the same random state because our data set was splitted almost the same way. But if I should change it to random state of maybe 100, I'll be getting something different. So all that's matters. So now we are done with that. And we have this another part. This is to print our shape. This, you can decide to include it. Is your choice. This is optional. So let's run this part. Then let's create another. This is output optional. This, but you can put it, this is to give you some other informations. Sorry, I didn't add it there. I just run the code. So this is, we splitted our train and test set, but we want to know the shape, the number of data that we have in train set and test sets. So that's why we have this. So let me just remove the optional. It's optional because you might decide not to put it. It doesn't mean your model won't train. Just like the way we have this there. If you didn't put this, you still run your model, but it's just as a way of visualizing what you have. So what you have here now is telling us our S train now has 90 rows of data and 4 columns. You can see the 4 columns here, 1, 2, 3, 4. You can see it here. So it's telling us it has 90 rows. In our test, we have 60. That means the total data we have is 90 plus 60. That is 150 rows. So our data set is having those 150 rows. So based on the 40%, 60-40 we splitted, that's why we're having this. Let me change this to 2 and let's see. We will see what will happen now. Then let me run this. You can see you're having 120, 30. So and your rows. So you can see that. So let's return it back to 0.4 that we have. So this is just to show you the numbers of, so you can even use that one to know. Sorry, let me run this. So you can use that one to know how many data sets you have. You can even run it in the beginning before you even split your data set to know the total number. Then after splitting, you still do that. So we are done with that. Then we move to handling categorical data. I mentioned this last section where we do what we call encoding. So now in encoding, we have 2 types of encoding. We have the label encoding, where you have labels like maybe cat, dog, bird, or so, and you convert them to a number. Or anytime you are seeing cat, give it number 0. Anytime you are seeing dog, give it 1. Anytime you have bird, give it 2. Anytime you have goat, give it 3, like that. You are just assigning a number to it. So that is, you are encoding the label. So you convert each of the category to a unique integer. I can decide that cat, just give cat 5 anywhere you see cat. This is label encoding. So this work well where you have a meaningful order. Maybe your labels is meaningful. So and you have another one which is the one hot encoding. So this is used to create separate binary columns for each category. For example, you have a cat. The cat, is a category now. For cats now, I can now create 2 separate columns for cats. That is, in cats, I have what is the value if it's not a cat. In cat, you can say this is not a cat, this is a cat. I don't know how to use the word now. Not cat and cat. Dog, not dog and dog. You can see that you're having separate binary columns for each category now. So that is another form of encoding. So it creates separate binary columns for each category. So with ones and zeros. So I think for our own, we'll be using label encoding. That is very simple for us to use. So you can see, okay, this is an output of one encoded features. You can see I'm coming. You can see this now. You can see 0, 1. You're only seeing 0 and 1. Yeah, I think let me use this example now. Let me use to explain this better. How many categories do we have in these features? Now you only have 3: cat, dog, and what? And bird. These ones are just repetition. Hope you are seeing it. Cat, dog, and bird. So now when we use one hot encoding, so let's say for the first one, we're having for the first row is what? Dog. So let's say cat, dog, and bird. So it will give 1 to that row. It will show you all the targets you have, all the categories you have rather. If you have 5 categories, it will show you 5 columns here. 1, 2, 3, 4, 5. It will show you all those columns for the category you have. Hope you are seeing it. So now in that category now, for the first row, what is the answer of the first row? If the answer of the first row is goat, it will go to the column that represents goat and give 1 to it. All other places will be what? Zeros. So it will move to the second row. What is the category of the second row? If it's a dog, it will go to the column that represents dog and give it 1. Then all the other ones will be what? Will be what? Zeros. So for example, now for cat, I think it gave cat the second row. It has 1. For dog, it gave dog the last row. You can see dog 1. The next one is what? Dog. You can see 1 here again. Hope you can see it. Then for cat, I said it gave it the second column rather. You can see cat again coming here 1. The rest are 0. So for bird, it gave it the first column 1. So now by the time I run my code and I want to predict now, and I'm having maybe this row, I automatically know this first column is for dog or is for bird. This one is for this one is for this. That is one of encoding. So you see that you need to, it will take some kind of I don't know how to put it now, to understand what encoding very well. So now, but for label encoding, you can just give random number, maybe between 1 and 10, between 1 and this. So anytime I see 1 or 2, I know this is what it means. Very simple. So that is for that. So now we need to perform one auth encoding now, because based on our data, you can see we have what? 3 setosa, vesical, vaginica. So which one do you think we should use? Should we use one auth encoding or label encoding? Which one? Which one should we use? Label encoding. All right. So let's use label encoding for that. So if you have this one, normally, because we are just doing it step by step. But assuming it's not step by step you are doing, if I know I will use label encoder, I could have added this one in the beginning, this from this. I would have added this in the beginning where we do import all our libraries from. But since I've run the code step by step and so I can just add this in myself. So from sklearn processing, let me just copy this step by step. Then I'll change some parameters here. V. And I'll do something now just to, that's why you must, if you know how to, you must understand your programming very well. It's not that you start writing everything word for word. That is the essence of we creating variable names. So now we are using label encoder to encoded features now. So for this now, this will be a categorical features. So what's that categorical features? Here you have setosa and this and this. And you can see that I've already defined them into what? Target names. So when you ask it to print target names, this is what it will print. So instead of me writing this place again, I'll just put target names. Hope you are seeing it, Control C. So let me just put it here. Instead of me writing it again, I'll just put that target name there because we'll define it in a variable. So now let's run that. You can see now it has encoded our feature. So the first one there in our setosa. So setosa is what? 0. Vesicolor is what? 1. And vaginica is what? 2. So you can see that. So now let's move to the next one. So we encoded our features. So we are now moving to training our model. And I mentioned something is in this ML notes 2 that I talked about, okay. In this ML note 2 contains some other aspects, chatbots, CNN, and the rest. Okay, yeah. And that's the classical ML machine learning. So this involves us, and we'll be working with decision trees where we use random forest and the rest. But we have linear regression and logistic regression. So linear regression is when we are predicting numbers, yeah, a unique number. So if, for example, if x increases by x, how much will y increase? Just like a question, it answers. But logistic regression, yes, you might be seeing the term regression, but it's used for classification. Because when we are classifying now, the way our model works, yes, we want you to classify whether this is a dog, is a cat, or that, unless you are using decision tree. So if you are not using decision tree, by the time it's calculated, it will still give you a number. And you remember I said machine learning is what? Probabilistic, not deterministic. I think I said it somewhere. And last, yeah, so because of that, it will give you a probability that this ML is probabilistic, neither yes or no. It won't tell you, yes, I know this is a cat. No, I know this is not a cat. It will just give you the probability. That is why even in the results we are using here, you can see in the final results, you'll be seeing 0.99 something. So it's based on that number. We will now look, oh, this is closer to which number? This is closer to which number? So that is if you use one not, I think one not encoding or something like. But let's still run our code. So logistic regression now, it will still give you a number. But basically, we use it for what? For prediction. Might be down anytime. So yeah, hello. Can we hear me? Hello. Okay. So I just need to confirm because my network went off. So I just had to quickly switch network. So now, all right. So as we were saying now, we're talking about the logistic regression part. So this is sigmoid function. You can just remove that. So now let's go back to our model building now. We need to build. So now we are using logistic regression. That is the reason why I had to mention that. Because it's a form of classification we are doing. So from SKL, we are importing a linear model. So, and that linear model we are importing now is logistic regression. We can decide to say we want to import linear regression. It's our choice. We have a lot of algorithms, a lot. We still have k-means, k nearest neighbor. The way the k nearest neighbor is, let's say you have, maybe next class we'll talk more about it because of time. So we'll be taking them little by little. By the time we start working with different algorithms, they'll combine algorithms and all that. We use it to solve problems. So now, and we have our mass iteration as 200. So then your logistic regression part, you use fit. You know, I said in the other part that you have model.fit. But now the reason why you're having logistic regression is that is what we define it. But I will try and change it to what we already know. So where is our code? Runtime disconnected. I need to. Hello, please can I know if you are still hearing me? I just need to be sure my network has not disconnected. All right. So now, okay, I'll bring this here. I'm importing logistic regression. So I'll change the name here. I don't want to use logre. Let me use model that we all know. Model. Then I'll change this to model. So that is why it's not like you need to use something that has been used before. You can just tweak your code as you want. Though we just have like some common thing that people use. So for even ML, most time we use model.fit, model dot. So that's I'm using model. So now model.fit. So now we are trying to train our model now. In our model, what do we train? We train it with what the train data set. And the train data set is what X train. When you are training it, you also give it the answer. But we are not giving it the answer of our test data set, which will lead to data leakage. No, we are giving it in our trained data set. You tell it this is the answer. This is why we call it a supervised learning. So we are supervised, we are giving it the answer to learn. Or when it has now learned finished, that's when we now ask it to go and test, to go and predict the answer of our test set. I hope you are getting it now. So by the time we now ask it to evaluate, it will now evaluate the prediction it does with the actual results that our test set. You know, in our test set, we also have the answer in our test set. So by the time we use evaluate, it will now start comparing it, what it has predicted with our the actual results. So now let's train our model. Now, in this place now, we can see when we are working with TensorFlow, we use epochs. When we are working with neural networks, you are seeing epochs and the rest. Even when you, in cases, sometimes you even be seeing what we call batch. That's in one epoch, instead of you taking all the data, if you have heavy data like that, instead of you taking maybe 5,000 data at once, then it will now go like that. It can take it in batches. It will take out of that 5,000, take some small batch, take it batch by batch. We also have things like that. But now we are not using epoch, we are using mass iter. So mass iterations. So it's just related the same way with epochs. That is numbers of time we want it to go through our data to learn. Hope you are seeing now. So the parameters, the mass iteration is 20. Okay. These are some informations. Class, random state, solver, and some other things. You don't need to bother yourself with that. Our own is it should learn. So you can see the classes. This is our encoder here. All right. This is our features. How many features does it have? It has 4 intercepts. I believe you know. Precious was there when I was trying to explain this thing, that I was saying these are normal equation we have in math. M is gradient, C is your intercepts. So, and when we now relate it to machine learning, we have what we call weight. Our gradient is our weight. That's why you have gradient descent or something like that. When we are talking about gradient descent, we are talking about adjusting the weights and bias. So our intercept is like what bias. So you can see intercepts here. What are you seeing here? AKA bias. You can see it there. So that is just part of the things that has been explained. So I'm coming. So now let's move to the next thing. So now we've trained our model. We know how to make predictions. We're using our what? S test. So now we want it to predict all the remaining part of our S test. Then we'll evaluate. You know, I said in evaluating, we'll now compare it with I don't know how to use the word now. We'll compare it with the actual results. And also another thing is, instead of me predicting, but because we want to evaluate our model to know as our model, because we just use now in this S test, I can decide to just give it for it to just predict a value and just give something like and just give it something like this. Predict the first maybe row in that S test. Predict the second row. But if you do that, that is when if you have a validation set, we'll use our validation to evaluate. Then we will now use our test set to start maybe predicting one by one and the rest. But now, because we don't have a validation data set, it's a test set we have. So it's our test set we use to do all that. Don't forget, I've changed this logistic regression to what? Model. That is why you need to understand everything you are doing in your code. So we'll predict our S test now. It has predicted this because we didn't ask it to print anything. So now let's go to evaluating. Let me just give this name. Let me just add some comments to them because it's good to always add comments. Predicting. Let me add another one here. Training our model. Training the model. So now we've predicted. So now let's move to evaluating our model. evaluating. So now in evaluating, I'll quickly explain some things. Evaluating the model. Let me check. I think evaluate. We have some evaluation metrics where we have the root. Sorry, let me enable scrolling. So we have the classification. Now in classification metrics, we have what is called confusion metrics. Confusion metrics is just like, where's the brush? It's just we having like a table. You have a table like this where you have something, you have this, you have this. Just like two lines here. Sorry, it's two. It's meant to be two. You have positive, you have negative, you have another positive here, you have another negative here. So anything that falls here, positive and positive, this is true positive. That is, this is false. Which one should we put? Okay, false positive. Let's use false positive. Or it depends on, you can even call it false positive or anything now. So this is our true, sorry, positive. This is our actual results. This is our predicted value. Or you can make this your actual value, predicted value, anyhow you want. So then this will not be what? This negative. Our actual result normally is meant to be what? Positive, and we're having negative. So this is false negative. And this is true negative. This now, you can also swap it now here and have false positive. I can decide to use, let me use false positive here. I make this place my true place, and I make this false negative. I think this one will be better. This is my true, this is my predicted. Yeah, this is the true value, the exact result. Why this one is the predicted. So I hope you understand what I'm trying to draw. So that is what confusion matrix is. So it's based on these things we can now calculate what is called recall, and precision. So let me just minimize, we'll be seeing them here. So recall, ROC recall, you can see precision recall. So we have the true positive. Precision now is true positive. There's a way you calculate all the true positive. All this, and we have type 1 error and type 2 error. They have cases, especially maybe when you are creating the classification model for detecting disease diagnosis. It has the implication of maybe a person has the disease and you're telling the person he does not have the disease. That is predicting a negative, meanwhile the person is positive. Is not really good enough. So in that case, you need to consider your false positive. You need to place priority on minimizing it, minimizing your false negative, yeah, because the person is not negative and is giving it false negative. So that is type 2 error. So if type 2 errors are harmful, just like in the scenario I've mentioned here, a model should optimize. So you should optimize for what? More recalls, minimizing type 2 errors. But in some scenarios, type 1 error, it might be type 1 error that is more harmful, just based on your model you are designing. You need to understand all that. So, okay, evaluation metrics somewhere. So I'm just trying to talk about the evaluation metrics, okay? False positive is type 1 error, okay, and type 2 error. So now let's go to evaluate our models. So you need to understand what is MAPE, root mean square error, and all that. So let's evaluate our model. So now we are going to evaluate our model we import evaluation metrics from scikit-learn. SK is scikit-learn. So now we are only dealing with accuracy. Most of the time, the most common evaluation metrics that we use most times is what? Accuracy and loss. You see in the hello world model that we did, you are having loss. But I don't think we have accuracy here, it's just loss. So if you most of the evaluation metrics that we usually use most of the time is accuracy and loss. But that is when you are designing a simple model. For a simple model, you can use that one to make your decision. But in some models, you might need more than that. Even this is giving me some prediction. So you might need more than that. Control Z. I want to try and see what it will give me again and say some things. But let me just, okay. Can accuracy score? Can you see? Is trying to import accuracy score. But let me just go on. So now our metrics of accuracy. So it's importing metrics. Then you can see the Y test. That is our, Y test. Now we have the target of our test set. So this is the target. And Y prediction, the one we just predicted just now, we stored it into a variable name called what? Y. We assign it to Y pred. That is targets, pre-predicted targets. You can see it here. So we want to compare these two together. We want to evaluate the accuracy of our model. So when you are using accuracy, you have higher accuracy, your model is performing better. But when you are using loss, in cases where you are using loss, now your loss need to be what? Minimal. It's not that when you're having a high loss. So in some cases, you can even use both accuracy and loss. Especially when it comes to I don't know, I've done more projects with TensorFlow more. In TensorFlow, we even use almost the two, accuracy and loss. That is why you see in this place, you will have defined all this in this model.compile. I'll put accuracy, I'll put some other things there. So by the time I'm evaluating my model, or even by the time I'm training my model, it's putting the result, because it will initially on its own start, it has tried to get like a sort of validation on its own, even before me now evaluating it. But let's run this. You can see we have what? 0.96667. What is the result they have? What's the result they have here? But something, I want us to do something different now. So can you see? Almost same answer. Who can tell me the reason why we are getting the same answer? You can run your own model and not get the same answer. Why are we getting the same answer? Anybody? I think I said that earlier. Hello? If you remove the random function, yeah, random states part. So you can see, because we are using the same random states, that's why we are having the same answer. So I can say if I remove this one, my code can still run. But when I remove this, the our code will just pick a value on its own. So in that case, we will get a different answer. Or if I decide to change the value that is there, we might get almost the same answer or a different answer. But the reason why we are getting the exact answer is because of what? The test set is not that we are using the same random state here. So it splitted our data the same way. So now, this is to tell us now, by the time you round this up, this means our model is what? 97% what? Correct. That is what it means. 0.97, just two digits, 0.97, and 0.97 times 100 means our model is what? 97% correct. In real life, oh, wow, this is correct, this is correct. It's actually good. Now, let's now verify. In this way now, you can now test your model. Now, based on what we did here, we said after you've evaluated your model, you can do what? You can deploy as API or app. Now, we can do like a sort of deploy here. Now, what I mean by it, you can say we want to predict, and I'll give it. You can see I created a sample was created here. They gave it the sepal length, the sepal width, the petal, they did like for 2 datasets and asked you to predict the actual species. So that is when you are sure your model is performing very well. So by the time you are sure your model is performing very well and you gave it another data, or maybe somebody is imputing a flower, or saw a flower and gave it the details. So I don't know the type of flower it is. At that time, you can trust your model because you know your model has done very well. So you don't need to even bother yourself. That's why you now see some models that, oh yes, you are trusting the answers and the rest. So, and there's a way now, they did something here now. Because if you predict, you'll be having 0, 1, 2, because we've encoded our data. But 0, 1, 2, I might not understand it. Let's say somebody, you use it in your back end, you need to create a front end. We won't understand what 0 means, what 1 means, or 2. So we need to what? Convert it back to what we know. So that is what is being done here. So you mark your target name for P in prediction. So it will match it and give us the what? The answer based on that number that we have. It will help us match the target name and give us the exact prediction. So, but before if we were to test this sample, we just use one of these data sets. I want to show the prediction that we have here. Y prediction, we want to show it. Let's print that Y prediction. Let's just print it out. We will see it's long, but okay, let me just print the first 5 rows out. Print. Control C. I want to actually see. I'll print 2 things out to actually see if it's right or not. Okay. I'll print Y prediction here. That is our predicted target. The first 5 rows, that's like 60 rows. So I don't want to print everything also. So I'll print the actual here, which is our Y test. So you can see now for the first 5 rows, the first row now, what we predicted, it's okay. Let me just change some things here. First 5 predicted targets. Predicted targets. Predicted targets. Let me remove predicted targets. First 5 actual targets of our S test. Okay, of S test. So we'll soon be rounding up. Just to finish this part, at least we know we've done something today. So now, so you can see in our first prediction, you can see that the answers we have is matching. You can see. So we can say our model is almost 100% accurate. 90. If you should have a model that is 100% accurate, suspect your model. Hope you are getting me. When your model is 100% accurate. I think I did a project like that and I got 100%. I was like, wow. It was at the end I discovered there was a data leakage. Yes, I removed the targets, but this model too is smart now. It can do some simple linear regression on its own or some things. Since I removed the target, even from the futures, that is why I think I mentioned it. Just go through all these sections we've done. I mentioned it in a section that in one of the first section or second section that we need to determine the futures we choose. In some data sets, we don't pick all the futures. That is some X columns. It might not be what you are predicting, but maybe your input. You might not pick all the inputs because you picking some input is like giving an int. The model itself will know if I add 1 plus 1 together, I'll get 2. So even though you are not giving it the answer as 2, you already has 1 and 1. You should just add it together and get your answer. You will not be surprised. Your model is performing very well. Then when you give it another data set, it's performed worse. And by the time you are training it, you've given it 1-1, and it's getting to you've given it, the model too will become smart. And so you need to suspect your data is having 100%. That is why you need to carefully select. If you know that from your data, just as if you want to calculate profit. Overfitting, thank you. You want to calculate profit. Even the model, to calculate profit, you do this, you do that. So that is just it. Now, this has the first one is, but we really want to know the actual label. It's just giving us number. We don't understand that. So let's see how we can do that to get the actual label. Okay. Predict species. So let me use this. Let me use this Control C to print the actual coming. I'm trying to see how I can use it. Let me first put it somewhere here. Predicted species, iris target. Okay. X. Let me put it somewhere here. Oh, for P in Preds, do you have prediction somewhere there? Oh, that is why. For P in maybe Y prediction. Sorry, Y prediction. For P in Y prediction, which is this. Then print, okay, predictions, which is this. Then also print, let me see if I can match the two together, or let me just leave it here. I'm trying to, that is why you must know how to manipulate your code. And if not, you can just use the Gemini here to actually help you out. Then I need to add something here. Oh, okay. Let me do this. Let me try and run it first and see what it will give us. So I want to check it's giving how many is here? How many in the first 5 rows, right? So it gives the first 5 rows. The first one is Setosa. This one is 1-1. So we should get the same answer. Very scholar. We are getting very, can you see it got very scholar twice? Then the next answer is what? 0. We are having 0. So 0 is Setosa again. We are having Setosa next. Can you see that? But this is printing more. I think I need to adjust something here and give it for the first 5 colon. I think so. Let me try this. Yeah, you can see Setosa, very scholar, Setosa. And yeah, this is printing the first 5. That's actually what I wanted to do here, but no need. So you can also do that for this. So this is what we will need. So because I don't to understand this, I'll need to start going back to my encoding part. So you can just do this. It will match it out for you. Then you add a loop there and it will do that for you. Hope you got that. Let's do for the actual also. Control C. So you have your Y test. So Y test, then you have this also. Then one more thing that we'll do, then we'll round up. So once we do this, we'll do the last thing, then we round up. Now let's give this one because they're having the same name. It has already been used. you want to keep overwriting stuff. Yeah. So you can see it here. It's giving the same answer. So it's matching this label to this. So we are done there. Then the last thing there. So now to predict, let's give it predict sample, then okay. Let us define that on our own sample. So we have 4 features colon. This thing is already predicting because this is something that is publicly available in the scikit, I think, website also. So that is why you can see it's all giving almost same thing. So now let's give our own value to it that we want. So let's say we give it the length is 2, the length 2. We have another one 1. We have 1, we have 5. Those 4 columns. We have this. I think even though this one is enough. Shouldn't give me issue if I just use one of these. Yeah. So now I want it to predict. So I'll come and okay, model dot predict. I'll name it sample prediction. Model dot predict this. Okay. S predict is our sample I call S. So predict, then we have model dot predict. Then we have our what? Our sample. Is there anything else? Is there anything else? There's an error. S test model dot predict here. Why is it not giving? This is an array type of data. Yeah, what is giving the error? Okay, I think the error should be from here. From the way, sorry, from the way it was created here. Okay. Can you see what caused the okay? Can you see what caused the error there? I hope you can all see that. Because I need this one is an array, so I didn't put all the brackets, everything there. So then print, it will print our S predict. Then after that, I want it to also do something. Print. I want it to also print the target name. Print the target name for, okay. Let's ask it to also print the target name. Arrays of target for target names in Control C. I hope you are still with me. All right. So we have S prediction here. I'll remove the 5 colon here. Okay. Okay. Let's see. Yeah, so it's predicting 0 based on the data. This one is, I'm done, I just gave it any data. We've tested our model, we see that it's performing very well. So I gave it an extra input anyway, and I asked it to predict. So it's predicting the class as what Setosa. So I believe we all got this. At least this is a great start to it. We just use logistic regression. So maybe in the next session, we use some other data sets. Now we will load our own data set in the next session and try and still use this logistic regression before we move to other algorithms. So we'll be having more sessions where we'll just be working on projects and all that. So I don't know if you have any question or anything that is not clear before we call it a day. Any question? Okay, no, not for now. What of Precious? Is there any question? So probably if there's no question, just remind me that I want to upload this code also to the drive. So in case I forget, I'll put the materials are already there, but I just need to add this last one to it. Then these two codes. We cannot go through it and use it as we want, load our own data set and all that. So we'll be rounding it up here to for this section. So if there's any question, you can ask on the group or anything. So thank you very much for joining tonight.